Okay. So, we had seen earlier that the LMS algorithm, the filter weights converge not absolutely, but only in mean to their respective optimal values as iteration index small n goes to infinity, that is we reach something called steady state, that is for large value of n. Typically, what we have there, if you take say any kth weight, we had already discussed this, I am just repeating. Suppose wkn and you are going through iteration, you are updating it via LMS algorithm, okay, particular weight I am considering. Its optimal value may be here, wk opt. So, initially it will fluctuate in any region, if you go like this. But in the end, it will fluctuating around the optimal one. So, if you measure the mean of this wkn at n very large n or as n tends to infinity like here, the mean will be optimal weight. So, we get convergence only in that sense. Then one can ask the question that how good it is, because if it is still fluctuates over a wide range. So, at any iteration I get a value much away, quite different from wk opt, because it is fluctuating over a wide range. How to control the range? How to make sure that the range is small? Okay. So, for that we require a second order analysis, that is we will take the error between wkn and wk opt, that is called filter weight error. This is for only kth component, all the components put together will be a weight error vector V n. We will take that and we will take the variance of each error, okay, and sum all the variances. That variance will give you the power of the fluctuation, right, because otherwise it can, I mean, if you do not take variance, if you take just the value, it can be highly positive, highly negative, when you add them it is 0. So, it can indicate that on the average value is small. So, we are happy, but actually not, because plus and minus both are there, that is so they cancel each other. But the moment you take variance, it is the difference between wkn and wk opt. So, that increment you are taking and you are taking the square of that. So, that positive increment, negative increment, you get positive value, positive power and their average. So, if that is less, then the range of fluctuation will be less. So, that is why the second order analysis, that is variance analysis of the filter weight error, okay, that is what we have to carry out, and that is a very tedious exercise, but I will not go through all derivations, because that is beyond the scope, but I will give some important results in between and then carry on with the remaining part of the derivation with that, so that you can develop an insight. All right. So, here I take the filter weight error vector, not with respect to a particular component, say kth component, but all together minus the corresponding opt, all right, V n. W n, as you know, we have got so all the weights, you have w k n here and w opt is the corresponding optimal vector. So, this will give you the filter weight error w k n minus w k opt, filter weight error for k equal to 0, k equal to 1, k equal to k like that, all right, this component. Okay. And in general, we are considering complex case. So, LMS algorithm, in LMS or for that matter any adaptive filter, say w n plus 1 or let me make it simpler, suppose you have got an adaptive filter, output error is E n, okay. Not necessarily LMS, what I am going to present is more general, just an adaptive filter, filter coefficient vector at any nth clock is this, you are updating them by some algorithm, adaptive algorithm. So, at the nth clock, the output error will be desired response minus, as you have seen, say W. Okay, let us consider a real case, because I remember I have not done possibly the complex LMS algorithm. So, let us carry on with the real case. So, in the real case, it will be W transpose n x n, right. W transpose n x n, this is a filter output, because this is the filter, x n goes in, this we have seen many times. Filter output is y n at any nth clock. These are the filter coefficients. So, this W transpose n x n means, and x n is the data vector. No change in definition, I am just repeating them. So, W transpose x n is W 0 x n plus W 1 x n minus 1 dot dot dot, which is the filter output, and W n is updated by some adaptive algorithm, fine. But at nth clock, W n is what? If you take this W opt to the left hand side, it is the W opt plus the incremental part V n. So, if you replace that here, it will be D n minus V n plus W opt transpose x n. All right. Then you take this in one place. What is W opt transpose x n? That is, if I have W opt here, then the corresponding filter output is W opt transpose x n. Okay, instead of this W 0 n to W n minus 1 n, if you have W opt coefficients like W 0 opt, W 1 opt, W k opt and all that, corresponding filter output will be that's W opt transpose x n, like it is W transpose or W n transpose in general case x n. If W n is W opt, it will be W opt transpose x n. So, when you are putting the optimal filter, you are getting the best case, because y n and d n, their difference E n has a minimum variance. That is how W opt was derived, that optimal filter R inverse P, that was derived by minimizing the variance of the output error between d n and y n. Okay, so, that is the best case. That time y n becomes a very good estimate of d n, because the error between them has then the minimum power, minimum variance. So, that is this, that is why I call it this also error, output error, filter output subtracted from d n, but this is an optimal error, E opt n, let me call it E opt n. And another term I have coming from the weight error vector term, V n transpose x n. All right. Therefore, what is the variance of this error? Variance. So, that is what we will work on in the next page. So, what we have is E n is this. So, let me rewrite again. What we have obtained is E n is E opt n minus V n transpose x n, where E opt n we have seen is d n minus the filter output with optimal filter as the filter coefficient vector. Okay. So, therefore, if I take the variance, expected value of this is real. So, no point in putting mod and square, because square itself will make it positive. So, E square n is this. This is a scalar. All right, this is a scalar. The square of it, I can always write like E opt n as it is, or to make it even simpler for you, I go through one more step. E square n, E n is a scalar, right. So, I can always say this is E n transpose, because E n is a scalar 1 by 1 matrix. So, its transpose is itself. Then if you put E n as this, it is E opt n minus V n transpose x n into its transpose minus, or maybe I put the transpose outside, minus the same guy transpose. And if you take down the product of these two, E obtained transpose, E obtained transpose is E obtained only. So, it will be expected value of E square E obtained square, that is variance of E obtained, because it is 0 mean and therefore, E obtained itself is the increment and squaring up and expecting variance. So, this is the minimum variance, because E obtained means output error variance is minimized. Then only you put W opt n and the corresponding error has minimum variance. So, if you calculate this variance, it will be a minimum thing, you know. Because I mean, if you square up and take expectation d n square, if you take expectation n will disappear because of W SSR. Similarly, cross terms also d n and x n, elements of x n, they are, you know, jointly stationary. So, again the cross correlations will have no n, x n itself, all the terms of x n they are W S S, okay. X n is W S S process. So, any correlation between them, you know, again independent of n. That is why variance is just a constant independent of n, minimum attainable. So, that is here. Okay. What we will show is this, except I mean in addition to the minimum attainable, there will be additional components, together will be this. This is happening because we are not using W opt when you are calculating E n, we are using some arbitrary W n, okay, which is updated by some adaptive algorithm. So, there E n is not just E obtained, an extra component coming due to the filter weight error, that will contribute to some additional variance terms here. That is what we will evaluate. Okay. This is fine. Then E of this cross term V transpose n x n E obtained, and okay, minus actually E of V transpose n x n E opt n, and minus E opt n V transpose n x n transpose, V transpose n x n transpose. Now, V transpose n x n, this is a row vector, this is a column vector. So, you got a scalar, and scalar transposes itself. Okay. So, this is actually equal to itself, because this is a row vector, this is a column vector, row vector into column vector is a scalar. Any scalar and its transpose, they are same. So, the scalar transpose of the scalar is the scalar itself. So, you can replace this by V transpose n x n. V transpose in x n is a scalar multiplied by another scalar E opt n, like here. So, these two terms are same, and there is last term is expected value V transpose n x n if I take transpose of this x transpose V, so x transpose n V n. All right. So, this is equal to minus these two terms are same. So, twice E, let me write V transpose n x n E opt n plus All right. Now, to analyze further, we make an assumption. We make a more generalized, we earlier obtained, I had what is called independence assumption, right. In the LMS analysis, we assumed that the current filter weight vector W n is statistically independent of the current data vector x n, and the reason we make the assumption, that was also the motivation was clear that time. I made it clear that time. We will just extend it here. We will assume W n is statistically independent of x n of course and also d n. All right. Logic is same. If you really write W n in terms of W n minus 1, W n minus 1 in terms of W n minus 2 and all that, and go up to W 0, which is an initial condition. I mean all the other terms, they involve x n and corresponding error E n, but E n will have again d n and x n, I mean x n, all right, and so on and so forth. Okay. So, this summation, as I explained that time, will be largely dominated by terms from the past, because that is majority in number, and past terms are usually uncorrelated with or even statistically independent with current terms. That is why you can say W n is statistically independent of this. If you do not understand, you just go back to my lecture, and that time go back to my lecture on LMS convergence analysis. That time I explained what is meant by independence assumption. So, it is just this. Okay. Just that time it was W n was assumed to be independent of x n. Okay. It was assumed to be independent of x n, and now d n has been brought into it. All right, d n has been brought into it. So, if that be, now you see E of 10, it depends on d n, it depends on x n, W is constant here. So, that means E of 10 is a function of d n and x n. So, here E of 10 is a function of x n and d n, right. Consider V n. V n is nothing but, what is V n? V n is nothing but W n minus W opt. So, basically you are subtracting a DC, a constant, from W n. Okay. So, if W n is statistically independent of x n and d n, so is V n, because V n and W n are equivalent. It is just a DC shift of W n by a constant W opt. So, if W n is statistically independent of x n vector and d n scalar, so is V n. Okay. So, here V n, it is statistically independent of x n, and E of 10 depends on d n and x n. So, it is a function of d n and x n, this is x n itself. So, this part is a function of x n and d n, this is a vector x n and this is a scalar E of 10, both are statistically independent with W n and therefore, V n. E of 10, because E of 10 depends on d n and x n, W is constant here, and d n and x n, they are statistically independent with W n and therefore, V n. Okay. So, E of 10 is statistically independent of V n and therefore, V transpose n, so is x n, okay, by this assumption. So, x n vector multiplied by the scalar E of 10, this resulting vector is statistically independent of this. So, expected value of, so what does it mean? It means, if I have suppose I need some space. If I had suppose two vectors x and y, they are SI, statistically independent, then E of x transpose y will be what? E of x transpose y mean first component of x, which is x 1, first component of y, which is y 1, x 1 y 1 plus x 2 y 2 plus dot 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 maybe x p y p, suppose length is 1 to p. Then E working on x1 y1 will be ex1 ey1, then ex2 ey2, exp eyp. It is same as, it becomes equivalent to E of x. If you take E of x first, that is E of x1, E of x2, E of x3, this vector, that transpose E of y. E of x1, E of y1. So, here you have got this vector E of x1, here top guy is E of y1, they are multiplied. Then next guy, this is a row vector because of transposition, E of x2, here E of y2, E of x2, E of y2. Okay, because statistically independent, overall expectation of the product is expectation of x component into expectation of y component. All right. That means, this will be expectation of V transpose n into expectation of this. Okay, expectation of x n into E of 10. This we can do. That means, it will be, let me call it, give a name, this, the variance. This will be having this component minus twice, have a look, E of this and then E of this. You can do this transpose, I think there was transpose. So, you can either apply E on V n first, then take the transpose, or first you do the transposition, make it row vector, then apply E on that, either way it will be same, into E of x n E of 10. Plus this, sorry, E of V transpose x x transpose V. All right. Now, consider this term, okay, x n E of 10. We know this should be 0. The vector into scalar, so scalar times every component, and this is 0, because under optimality condition we have seen the current optimal error, it is orthogonal to, that is uncorrelated with each component of x n. Okay, this again you can see, you can write like E x n and E of 10 is d n minus W transpose x n, and W transpose x n is same as x transpose n W, and then x you write E of x n into d n, that is p vector, minus E of x n x transpose n, W is constant, so it goes outside, E of x n x transpose n, that is R and W. So, it is W opt under W opt, because it is E of W opt, and W opt is R inverse P. So, P minus R inverse P. So, R inverse cancels P, so it is 0. That this is exactly what we did last time. All right. So, these two terms goes, so I am left with this much plus an extra component. Okay. So, because I did not use optimal weight, optimal filter, I used just any arbitrary W n. So, overall output error variance has gone up from the minimum attainable by a factor, this extra factor. But remember one thing, by your independence assumption, W n and therefore V n, that is statistically independent of x n, right. Now, you can see one thing, that suppose as an example, a side story, Suppose I give you two vectors, okay. A, B is one vector, maybe alpha, and I give another vector beta as x, y, and it is said alpha, beta, they are SI, suppose given. This is V transpose, sorry, V transpose, and it is given something like this, E of like alpha transpose, like V transpose, alpha transpose, then beta, say beta transpose, and then again alpha. You can do one thing, beta beta trans, I mean what will happen is this, we have got A, B, alpha transpose, beta beta transpose and alpha, so again A, B, and beta beta transpose will be x y column vector, x y row vector, it will be x square, x y, y x, that is x y, y square, right. And now x square into A plus x y into B multiplied by A. On that if you apply expectation, so that will be, you know, because alpha and beta are statistically independent, E will get separated. It will be like, you know, I mean, it will be like this term E of x square A plus x y B into A plus again B into x y A plus y square B. This E will act separately on x square, x y, again x y and y square. Another E will be work on A into A, B and all that, okay, B into A, it will be like that, okay. You will see same thing if I keep one E, like, you know, this is E with respect to both alpha, beta. Suppose I keep E with respect to this alpha out. So, keep it as it is. Here you apply E beta x square into A. Okay, so, because E beta is only for x y components, so it will work on, and I could separate out because they are statistically independent. E alpha beta is E alpha E beta. So, E alpha beta, if I apply on this, I take out E beta, okay, overall E over this will be what? One expectation with respect to x y, that is beta, another expectation with respect to alpha, A b, they will separate out. So, the one with respect to beta I am directly applied here, E beta x square A, again E beta x y B, and similarly B E beta x y A plus E beta y square B, all right. This is what I am doing. But this is same as though I am applying E beta here, E beta on this, E beta x square, okay, into A into E beta x square into A, again E beta x y into B into A, okay, this is A. So, A E beta x square, so E beta x square into A, E beta x square into A plus E beta x y into B, E beta x y into B together times A, okay, plus B times within bracket E beta on x y, E beta on x y into A plus E beta on y square into B. I am able to separate out E alpha beta as E alpha into E beta because they are statistically independent. Okay. So, then I can write like this, I mean I can keep E alpha out and push like this. Okay. So, on the inner thing this matrix I apply E beta, which is restricted to the elements of beta, and then carry out the product, then apply E alpha. The same thing I can do here, because here instead of alpha I have got Vn, so alpha transpose Vn transpose, and instead of beta I have got Xn, but elements of Vn and Xn they are statistically independent because of the statistical independence assumption. So, same thing here. So, which means I can write as E with respect to V if you want, V transpose N, E working on this, and E working those will be input autocorrelation. Okay. E with respect to X working on this will be what? Nothing but input autocorrelation. So, V transpose N or V N. This product I have to now carry out, which will be a scalar, that have to take expectation with respect to V n, elements of V n. Okay, that will give me this extra component. This I will analyze in the next class. Thank you very much.